Jnanam paramam dhyayam. Knowledge is supreme.
Hello students, welcome to the final section of this course wherein we will try to discuss control topics related to batch processes. So far whatever we have seen, mostly we consider that processes are continuous, even though I did not mention it specifically. Most of the times we are looking at things which are steady in terms of time, or the objective is to keep the things steady with respect to time. So in this particular section we will see how things differ when it comes to batch processes. In fact, batch process control is little trickier compared to continuous processes, and we will see how that is done. So in terms of objective in this week, in this section, what we are going to do is, first we will try to differentiate how batch control is different from continuous processes. Later on we will see when it comes to batch, there are different types of control tasks which have to be incorporated, and we will also see how those connect with continuous processes. And lastly we will see how these things are implemented in a real controller, and we will also see that some of these portions would also carry forward to continuous processes. So let us get started. So when it comes to batch, the main thing that distinguishes a batch process from a continuous process is that batch process is inherently dynamic. So things keep on changing as a function of time, things are not continuous per se. What I mean by that is you always have a start and stop type of behavior in a batch process. Because of that you make things in discrete quantity or discrete quantities, and every batch can in principle mathematically be different from each other. However, the operational objective is that every batch has to look exactly same as the previous one. That is when you have a consistent product. So unless you have some sort of automation into your process, you cannot ensure that every batch which you are producing at different time of the day comes out to be, and operated by different operators, comes out to be exactly the same. So that is one of the major objective of a batch process, that you want to ensure that every batch has a consistent productivity, product specifications. And the second one is, as you are making different products, typically when you have a batch process, one of the reasons the way you can incorporate, one of the reasons why you have a batch process is that you have sort of seasonal production, or you make multiple products using similar type of process synthesis route. So you lot of times end up sharing the same sort of same reactors or separation equipment. So typically in a batch process you are given some target on a monthly basis, and you have to ensure that within that month you have to plan your batches such that you get the same the desired amount of different products ABC or whatever you are producing using the set amount of equipment. And that is typically known as, that sort of problem is known as the scheduling problem. Typically it is a sort of a higher level problem compared to a control problem per se, but lot of times there is an interaction between scheduling and control. And lastly, you also want to do all this while consuming minimum amount of resources, so there is sort of an optimization also built in. So when I say that when we see last week we had seen that the advanced controllers are used to optimize a certain economic performance. So some similar optimization based controllers would also be present for a batch process as well. In terms of how batch processes differ from a continuous process, the main difference between a batch process and a continuous process is that there is a frequent startup and shutdown in a batch process. So let us say if I want to compare a batch and a continuous process, so in the continuous process, let us say a refinery or any petrochemical operation, what you do is you typically have a startup of that particular process. So when things are, let us say, warm, or you can say dry start, So there is nothing operational, that is like a shutdown state, and then you bring all the things to the operational level. And then you try to maintain the operation at that level for as much amount of time till you have a planned shutdown. So this will be, so this is a startup and this is a shutdown. Now here I am saying that things remain steady throughout this entire course, or what I want to say is your objective is to maintain things at that operational point. Sometimes there will be minor variations around this point depending on what advanced controller is telling you, and but more or less what you will try to do is you can easily distinguish there are two different points. One is a dry point where nothing is operational, and there is an operational point where you are going to get product. And this difference between the two, so let us say if startup takes about a day or two, similarly shutdown will take a day or two, and in between the process may operate for months to years till you take a shutdown. So you can see that the startup and shutdown are a very rare phenomena in a continuous process. So this is for a continuous process, and most of the times the operator sees a steady plant, and the objective is to maintain the production or the plant around his nominal point. And that is why all the controls studies which we have done so far in this course, the objective was always to have a set point and try to maintain that set point in the presence of disturbances, and some small set point changes which are governed because of some advanced controller, which are dictated by some advanced controller. When it comes to a batch process, however, what you have is you have a dry point, and then you have a startup, operation, again shutdown, you come back, and you can see that every time, every cycle or every batch, so let us say this is batch 1, batch 2, so every batch has a startup, small startup time, small shutdown time, and small operation time. This is startup, this is shutdown, and this operational phase. And you can see the magnitude in terms of the relative time of these three phases, they are relatively of the same order when it comes to a batch process. Now I am talking about a very general batch process. There can be some batch processes where the operational phase goes for about a day or 48 hours or so, but still more or less it is still within some hours and not as big as months or years. So you can see that the batch process always things keep on changing as a function of time, and that makes that makes control problem little tricky. So what we will do now is, so in terms of how we end up controlling such kind of a batch process, or how do we, rather than control, let me talk more about operation, because control becomes part of operation, how a batch process is operated and what sort of control system, what role control system plays into it. So essentially there are four key tasks which any operational or control system has to perform in a batch process, and I will also try to connect how these parts relate to a continuous process as well. So the first part is known as a sequential and logic control. So as the name suggests, it deals with sequence and logic. So this deals with the startup phase, as well as the shutdown phase. So the activities which you have to conduct in a startup phase or and a shutdown phase, those would come inside the sequential and logic control. And same way, if you want to connect with the continuous process, the startup of a continuous process as well as planned shutdown of a continuous process would also involve such kind of a sequential and logic control. The only disclaimer here is that these kind of control logic will be activated only during those startup and shutdown times, but most of the time these systems would sort of remain idle because the plant operates at its operational point in a continuous plant. However, in a batch process, these sequential and logic control gets activated during every batch, and what it does is it allows you to, or it ensures whatever are the tasks which have to be performed in a batch, which typically is maintained within what is known as a recipe. So every batch has a recipe which says that mix A and B and then heat the reaction mixture, wait for some time for reaction to take place, and then start removing the product. So all those things. So in a batch process, generally it is based on these different steps, and these steps have to be carried out in a particular sequence. So ensuring that particular sequence in an automated fashion would be the job of a sequential control part. And there is also sometimes there is logic associated with it, that you want to make sure that when you are adding something, some other things have to be specified, some specs have to be maintained before the product is removed. So there is also some sort of a logic associated with some of these steps. So all this sequence as well as logic for a batch recipe would be incorporated using a sequential and logic control. So mostly this is a binary logic. So along with that, so all it deals with are three types of things. So one is sequence of actions, what we saw. The other thing it has to ensure is safety interlock. So safety interlock means you have to ensure that while the steps which you are going to take, they ensure safety of the particular process, people who are around it, as well as safety of the environment. And there are generally safety constraints associated with it. So unless those safety conditions are satisfied, you will not move on from one step to the other. So all this sequence, the logic around that sequence will also be dictated by the safety conditions, and sometimes there are also conditions related to the process. So there will also be some process interlocks. An example of that would be you would not start mixing unless there is certain level inside a particular vessel. So you do not want to move. So let us say if you have a vessel and you want to start the impeller, you will not start it unless there is a certain minimum level. So this is not really a safety related interlock, but it is more of a process sort of an interlock, where you want to say that the task of starting the impeller should be done only when there is sufficient amount of level inside that particular vessel. Similarly, if you want to withdraw product, similar thing would be there. You will start withdrawing the withdraw the product unless the level is above a certain value or so. So all these things, this mostly falls under logic part, and this is more of a sequence. So all these sort of actions would be considered or would be part of this logic, which is known as sequential and logic control. So let us now take a very simple example of mixing or batch blending to explain you how this sequential and logic works and how it can be implemented. So we will take an example of a batch mixer. So this is a mixer which is going to mix two streams. One is A and the other one is B. It also is provided with an agitator, and there is a way to remove the product, which we will call as A plus B. Now let me explain you how this process looks like. So, in this process what it says is, first the operator, in order to, let us consider this is the only process which you want to operate. So, the operator has to start the switch. So, this is known as a hand switch. So, operator will press the button. When the operator presses the button, this particular valve VA will open and it will start putting material into this particular vessel, and the addition will be done till a certain amount of level is reached inside this vessel. So, let us call it as LH. So, till the level reaches LH, you will have addition of A. Once the entire amount of A is added, the level is LH, at that time you will stop this wall or close this wall, and the second ingredient, which is B, will start entering the vessel. So, again the level will increase, and now you are adding B into a pool of A. So, you want to mix it. So, the agitator will also switched on. So, if this is a motor, then this motor will also be switched on when the level is above LH, and addition will take place till your level reaches a certain point known as LHH. So, when the level reaches LHH, you have added the required amount of B as well as A together, everything is mixed, and now you would start with, so now we will start withdrawing the product. So, this third wall, so let me even name all of these walls. So, this is known as a VA wall, this is a VB wall, this is a motor, and this is a VC wall. So, when the level reaches LHH, you will close the VB wall, you will open the VC wall so that the product can be removed, and while removing the product you want to ensure that still the A and B mixing is there. So, the motor will keep on running even during that time, and the product will be withdrawn till the level reaches a minimum value of LL. So, when the level reaches LL, that means you have removed the entire product. So, while the VC will close as well as the agitator will also stop. So, now for correctness, let me show that this level is like this, so that the agitator is always below the minimum level. So, that is the process. So, now let us see how, so you can notice that this process has lot of steps, it has some logic as well in terms of up to what point you should be adding a particular ingredient, and then what time what are the two things which should be together, for example addition of B as well as motor, what things should not be together like VA and VB should not be open at the same time. So, all these things are there. So, how do you ensure this automatically, how controller will make sure all the things operate in the correct sequence. So, that will be the part of sequential and logic control. So, for that what the process needs is some inputs from the system. So, for this system there are three things the controller need to know in order to decide what should be done. So, the inputs to the controller are the status of the process. So, which things would give me the status? What is the level inside the tank? So, that is LHH, whether it is LH or LL. So, typically every one of these would be associated with a binary signal of 0 and 1. So, what it will tell me is if LHH is 0, that means the level is below LHS, when LHH is equal to 1, which means the level has reached LHH. Similarly, for LL or LH. So, those are the three things which will tell me where my level is lying. So, let us say if LL is 1, LH is 1 and LHH is 0, that means I am above LL, I am above LH and I am below LHH. So, I am somewhere here. So, that way using these three tags your controller will know where exactly your process is, and there are four things which the controller will control. So, outputs from control will be the things which you can manipulate in this process. So, which is valve VA, VB, VC and this mixer M. so this motor M, so that the valve can be opened or closed and the motor can be switched on or off. And for simplicity we will consider that these valves are on off type of valves. So when I say VA is 0, which means valve is closed, when VA is 1, valve is open. It is not necessary that it should be the case, you can also have a valve which opens by a certain percentage, but for simplicity let me just consider that all these valves are also binary and the motor is also binary in a way that whether it is on or off. So, the first thing in order to incorporate this is you need to ensure that or you need to formulate what is known as a sequential and logic diagram or sequential functional chart, which tells you what are the sort of actions which are going to happen sequentially, what actions are going to happen parallelly, what are the different steps inside the process. So, let us see how such a kind of a diagram can be drawn for this system. So, here is a sequential function chart for this particular system, and you can see that it starts with this point where there is a push button which the operator is going to push. So, when the operator pushes this hand switch HS, 1 is a value which goes to the controller, and when the value is 1 it will open the valve VA. So, when it opens the valve VA, it will start filling the material A into the tank, the level inside the tank will keep on increasing, and when the level reaches the value of LH, at that time two things are going to happen. So, that is why it is shown as a parallel tracks after this. One is you will start filling B, for that you have to close valve A and you have to open valve B, and parallelly you also have to start the agitator. So, the motor will also start. So, these two things will go on parallelly. Within this left side arc, when the level reaches LHH, at that time you will start the discharge. So, you will have to close the valve VB and open the valve VC, while there is no condition in terms of there is no change of status for the mixer when the level is LHH, because you have to keep on mixing even though the product is discharged, and you will again converge these two lines when the level reaches LL. So, when the level reaches LL, at that time you have to stop the operation, that means you will close the product valve VC, you will stop the motor, and the signal which will go back is 0, that means the process is stopped and it will go back unless you push the hand, or unless the operator pushes this button, one will not go forward and the process will not start again. So, that is how you can draw a sequential functional chart for such kind of a system. And in order to incorporate this in a real controller or a hardware, we use programmable logic controllers, also commonly known as PLCs. So, these PLCs would execute the desired binary operations, all these sequences based on the signals which come from the process. Like here you are getting these inputs about the level inside the tank, and accordingly it will give signals to these different valves, and which will be executed in a process. Here I am saying that these are mostly binary logic, but it is not necessary. Nowadays these PLCs can also execute non-binary operations in terms of a control law calculation. PID controllers can also be implemented inside PLCs. So, let us now see if you really want to incorporate this into a programmable logic control, how do you go about it. So, what the logic which this PLC controller uses is known as a ladder logic. So, it uses ladder logic, and it is essentially a ladder. So, all of you know what is a ladder, and ladder has different rungs. So, every step in a ladder is known as a rung. And each rung will have a certain logic or step associated with it. So, if you say these are rungs are numbered as 1, 2, 3, 4, then every one of those lines will have a certain set of code which is associated with it, and there will be an output at the end of it. So, the output will be at the end of this line, and there will be some conditions with respect to different variables of that particular system, and there are two types of two basic types of logic actions which are done there. One is something which is known as a normally open contact, which means unless this particular variable becomes 1, this line will not get connected, this line will remain open for a binary of the variable value of 0. So, when you have a normally open contact, so if tag is 0, it is open, if tag is 1, then it is closed, and the idea is if this particular thing is closed, then this output will become 1. If the entire thing is closed, and if there is some discontinuity and everything inside this line is not closed, then the output will be 0. So, that way any piece of action will be executed along a rung, and then every instance of the controller, it will go from one rung to the another till it reaches the end. So, there may be some 1000 2000 lines of or rungs inside a programmable logic controller. So, during every execution of a PLC, it will go through all these steps and then come back. And just for your information, typically the cycle time is about some milliseconds. So, you can see that these actions are take place very fast. This execution of these different rungs takes very fast, and typically the cycle frequency of these PLC controllers is of the order of milliseconds. And mind you, these rungs are generally thousands of rungs are there within a single PLC. So, let us try to see how this PLC can be used to incorporate the sequential and logic control for this particular batch blender. So, we will take a short break, and when we come back, I will actually show you on a simulator how this can be done. It is a freely available simulator. So, I will show you how you can access it, and we will see how this can be implemented for this simple example. So, we will take a short break here. Thank you.